So now we've talked about the different levels of protein structure, but how does a protein get to that point? Is it as simple as just lining up the amino acids, synthesizing the protein, and everything comes to be as it's supposed to be? And the answer is that it's not quite that simple, right? Protein structure is highly specific to its task. It's determined by the amino acid sequence, but also all those interactions between those side chains. And in order for the protein to be assembled properly, it has to be encouraged for those interactions to be guided to one another, basically, right? It needs a little bit of help. And as we can see in the different types of a protein, be it its native protein, which is its functional, natural, active, three-dimensional, properly folded state, versus its denatured state, we can have very different protein properties, even though the amino acid sequence is identical. And this is a really great example of it, is the denaturation of ovalbumin egg white protein. It's the same molecule, right? It's the same protein, whether we have raw eggs or cooked eggs. And heating changes this dramatically, right? It fundamentally changes the character of the egg proteins. They look different. Why does this happen? Well, this is from denaturing the protein. And so the raw egg is the native state. It's the properly folded state. It's the way that the body creates, or a chicken body creates the protein. And when heated, some of those interactions between the protein are overcome and start to swell, and it just changes it fundamentally as it denatures the protein, right? The native protein is shown here on the left. This is the raw egg, and the denatured protein, which is what happens when heat and stress overcome some of these interactions. This permanently changes the structure of that protein. And so in order to encourage the native state, proteins need to be folded properly, right? There's a lot going on as a protein is created. It's not just the amino acids that come together in order to make a properly folded protein. There are other molecules called chaperonins, for example, that facilitate correct protein. And here's an example of such another molecule. It's another protein, and it facilitates how a protein is made, right? It holds it in the right way so that the folding occurs properly. And in addition to temperature, pH is essential as well, right? Without the right pH, protein folding won't occur, and we could denature a protein by changing the pH as well. Okay, this is a really advanced science, and again, this is one of those things where you could spend your whole life focusing on protein structure and folding. So what are the takeaways that we really want to learn for this course? Structure determines function. Yet again, we're discussing that structure determines function, and this structure here is not just the pure amino acid sequence, but it's how things are folded together, right? The interactions between the peptide chains, these are what determine the native versus denatured protein, where they have been ruined in the denatured form and they are still maintained in the native form. Other molecules are required to help it along, and this is key to understanding protein synthesis, is that this doesn't just happen. Our bodies have really complicated ways to ensure the proper protein structure is made in order to ensure this really intricate protein function. Heating can ruin proteins through denaturation. Change to pH can do this as well. And finally, that when a protein is denatured, it's pretty much irreversible, right? We can consume egg protein, break it down into its amino acids, and create new proteins, but there's no way just by cooling to change that cooked egg into a raw egg. We can always denature a protein, but once denatured, it's almost impossible to get that protein back into its native state. There's no way to uncook an egg. There's no way to make those protein chains find each other once again in the complicated way that the body has synthesized that protein.